Good. So we know now the binary is a little bit worse than the others, right? Already 2 to the 2 is way better. But when we have 2 to the 8, we have to do a little bit more complex calculation. Our encoding vector is bigger, but we don't have to retransmit packets or more packets because of the linear code. We come back to the example once we clean this up here on the side. Now for the recoding potential, I told you last time, if you have any given data over here, where we look into portions of G bits, which was my symbol at the time, you have the coding coefficients over here, and you have a new form of data, new coding coefficients randomly, always the same. You just code it together. We have done the last time. You put the two new randomly chosen values over here, and some header, which is some protocol header that you would put there. So let me show you why this is a good idea, right? Here you see 2 hops, right? You have one sender here, one receiver here, and you have 50% losses. It's dramatically 50 losses, but if you have Wi-Fi, for example, and you measure the losses, it's around 40 to 60%. You will not see the losses because they do retransmissions. But if you do multicast, broadcast in Wi-Fi, you see a huge number of losses. So what you see here is we would like to transport a certain number of packets, 4 packets. So when we do it with no recoding, just forwarding the packet, what the standard way in the internet is, then you have one packet, send it over, he will receive it, he will forward it, everything's fine. Now we send it again, he also forwards it, oh, this time it just did not work. So then we do P3, did not work, P4 did not work. Now we could use coding from the sender side, whether this is a Reed-Solomon code or if you use RLNC, right? It doesn't matter. Then you send out coded packets, and you have to send a lot of times until you get 1, 2, 3, 4 successful packets here. Overall, it were 23 transmissions. Okay, this is just forwarding it. And if you want to understand the success probability of a packet, is 1 minus epsilon 1 multiplied 1 minus epsilon 2 in this case. Okay, so when we do the recoding, sorry, the other one was the coding, this is the recoding now. We have this coded packet with the coding coefficients. Now you choose new coding coefficients and put them just here. You code this together with a new coded packet, and you have a new encoding vector over here, the new protocol header that you have to read out here and build it, right? This is not so much of our interest at the moment. We only look into that. Just by recoding, the encoding vector does not explode or it's always the same size. And the coded packets, whether they're recoded or not, always the same size as well. So this is what we did last time. Now what you can do is you just send them, and here you see same error probability. You send something that went through. Here it did not went through over here. Here he's sending something, it stopped at the relay. And last time he could not send anything, right? Now what we say, okay, let me recode P1 and P2. This is what I received so far. So I'm coding this together, send it over here. Then the next one does not come in. So this one here is a new linear combination. I'm sending it, went all fine, right? Now if you look into this, you only need 15 packets to transmit. And suddenly your error probability changes. It's not a combination anymore. It's 1 minus epsilon 1, 1 minus epsilon 2. So you only have to understand who is the worstling here. So in this case, both are the same. So here, the probability that you get something on the other side is 50%. Before that, it was only 25%. The question is, this recoding here, can it be done even without recoding? Can you get the 15 transmissions also without recoding? Yes, you could. Then you have to do something like this. You send all the packets to one side, decode, encode newly, send to the other side. Now you also have 15 packets. It's the same probability. So why is recoding so interesting for us? It's the same amount of packets. Capacity-wise, the same.
You don't have to wait till packet 8 to get the first packet on the target.
So it's latency. It's just latency. So we are, if you've heard the lecture Comnets 3 about 5G, or also in the Comnets 1, we talked a little bit about this 5G. Latency is so important. With every time you do a full stop here, which is in switching mode, message switching, you will understand more latency will be there. So if you look at this, a source, a destination, and a repeater with two different erasure rates, epsilon1 and epsilon2. When you have an encoder and decoder of Reed-Solomon, LDPC, LT, Raptor, even network coding, if it's only at the end with a repeater in the middle, the store and forward activity of the repeater will end up in 1 minus epsilon1 multiplied 1 minus epsilon2 as the resulting success probability to get the packet to the other side. With network coding, when you do not at the endpoint, if you have RNC here, we said it's the same, but if you switch on the recoder here, you get the minimum of 1 minus epsilon1 and 1 minus epsilon2. This is compute and forward. So before that, we just took a packet and sent it to the other side. Now we collect the packets, we do something with it, and then we send recoded packets out. And this, we improve our situation here a little bit. How much, you will see later. So that is the minimum of these. Why is this correct? We talked about this already in the very first lecture. We talked about the min cut max flow. So if you create a cut here and a cut here, what is the min cut? This is the min cut. Okay? So you get the best out of this. And now don't imagine of 2 hops. Think of 5 hops, 8 hops, 10 hops. So if you go from here to your favorite newspapers like Spiegel Online, FAZ, 13 to 15 hops. Okay? And if you collect all the errors, okay, in Wired it's not so bad, but if you collect some of that, interesting. Now, again, as an example, you can go and play around with that. Here you see the idea, you have an encoder and a decoder. The only thing you have to know, we don't have something called a recoder. So a decoder acts actually as a recoder, okay, in Codo language, so to speak. And what we do then is we do a simple forwarding. In the forwarding and the recoding is only in the matter of the protocol. So if you look at the example, what you do is you say, okay, I created an encoder somewhere up here, and now I clean up decoder 1 and decoder 2, where decoder 1 is our recoder, right? Was it correct? Yeah. So then we say, okay, while the last decoder does not say I'm complete, I go in and say, go to the encoder, give me a packet. I count the number of packets up. Now I have a random choice of epsilon, which is given up there. And if this is equal to success, then I will read it into decoder 1. If I was not successful to reach my decoder 1, which in this case is a repeater, I just start over again. I don't continue. You see, this means go back again in case I had a mistake. Only if I'm successful, I would go to the next one and say, okay, now decoder 1, you give me a packet. So here you put the packets into the decoder. Now we go to the decoder 1 again, give me a packet. And if there's success on the second link with epsilon 2, then you give it to the second decoder. And then you start up with the while loop again. So this is the repeater. And the recoder, if you look at this, it seems more or less the same, right? The only thing that goes away is this. Continue. So with a repeater, when I don't give something to the repeater, I stop, I go back. Here, I would say, okay, do we have success? Okay, I fill it into decoder 1. Nevertheless, I also would like to go to decoder 1 and say, give me something out, and I try to pass it over to decoder 2. So, and if you look then into what happens here, you can easily see what the theory tells you and what your simulation tells you. You can play around with this kind of simulation steps, for example, and try out what happens here. But you see really the recoder helps, yeah?
What does the follow library do if it only has one packet So if it gets successfully the first packet, then it transmits the first or recodes it.
Yeah.
But then if it fails to get the second, it only has one packet.
It will always give you the same. That is easy because the decoder is made in a way it does not have to overthink your protocols. It will only say, if you tell, give me a packet, then later we will exactly work on this topic. Whether we can or cannot, or should not, send out packets of a recoder that we have already asked 10 times. We know that this is stupid to do that, right? So you can make it a little bit more intelligent, and people worked on this. They just said, okay, why should I send out something when I know he has nothing new to say? If you know, for example, you could ask, right, decoder 2, rank. You can ask, what is your rank? Let's say you magically know that, and you know that this rank is equally high as this rank, then you would not send. You have nothing new to send. You can send a new linear combination, but this linear combination will be linear dependent per se. But sometimes you don't know what's on the other side. That's the point. Signaling that is the problem, and you will see this later. Now, when we did this, back in the time we did not have this nice notepad, we use Kodo, right? And with Kodo, what you can do now is to test this out. And people tried it out, and there was one lady coming to us and said, yeah, the theory does not hold. I said, why does it not hold, right? We tried out all the combinations, and it was always working what we said, what we calculated. And she came up with a counterexample. And the counterexample was, she said, I have 80% losses. So we said 20% losses and 30% or 20% loss on the thing. She didn't understand and made 80% losses on the first link and 80% on the second link, which is quite high. And suddenly the theory, our theory at that time and the practice did not match. And this was, here we see something, we said, okay, how many packets we have to transport over a 2-hop system when we have different erasure rates, right? And you see in the beginning when you have no losses, there's the minimum packets, the generation side, but if you increase it, then you have to send more packets. Easily understood. And this was theory. And then we did the same with our Kodo tool, and actually it was the same, or it looked the same. When we subtracted theory from practice, you get this, which we call the Sharkfin. So this is the difference between theory and the practice. So when they are not the same in this area or this, everything is fine. So when you have problems to fill up the recoder, it's not a problem. He will just take whatever he has, he send out, it's linear dependent, but it doesn't matter. Okay? The other side, if you fill him up quickly, and he always his rank is way larger than the other, also not a problem. But when they have more or less the same error rates, and especially if the error rates are quite high, here in the back, then it matches, because then he would like to send something, right, which is already linear dependent by definition. So this was a little bit more complicated to find this out, and we cleaned up the theory, but it was not the min cut anymore, right? You run the coding queues empty, and therefore there's nothing you can do. And there is a paper, you can look at it, how we did it. We said in certain cases it can happen that you, it's not about the code itself, it's really about the of the queue that you have and what you can code together. And with the new theory, what was here and what we measured, it's exactly this one. So it tells you a little bit it works. Nevertheless, if you're not in these strange areas down here, what we had, if you look at this coding example, I told you already it has to do with the min cut. Just to let you know, what you see here is, okay, when you have in the case of uncoded, right, then you have more or less 50% losses on this link. And with recoding on all of them, what would you get? What is the chance to go successfully to the other side? You just have to apply the theory, right? 70%, correct. And where do you have to put the recoder? Strange question, right?
B, and C.
Exactly. If you do it here and here, okay. But what happens if you only put a recorder here and not here? Then you would get the combination here, right? It's 80 by 90 is 28% losses. It's less than that. So whether you put here a recorder or not would not have an overall impact on that. It has an impact on the number of packets you're sending around. But in this case, it's a tricky question, right? Where to place functionality. So here it's clear, right? It's because there's the biggest hop. If this would be, let's say, 0202 and 03, then you would even put a recorder here. Otherwise, you will have to combine these to 80 by 80, 36% losses over here, and then this is larger than that. So the thing is really where to place recorders. And why is this? Why don't you put the recorders all over the place? Of course you can do that, right? That's the best what you can do. But on the other side, two things. You need computing at that point. And once you switch it on, you can ask Sue about it, you will need maybe more time in doing the computing. So there is a trade-off in whether sometimes forwarding is good, sometimes recoding is good. In theory, you should place the recoding all over the place. But in practice, where the placement of the recoder is a good thing. So here again, what we had before, here's the cut, right? So the min cut is 0.7. I just put it there so that you have a good feeling, and when you look at the slides, that you can learn something. Now, here's another thing that we used sometimes in industry talks to say where the problem comes from. So imagine you have a source and you have a destination, you have 10% losses all over the time. Forget about the Sharkfin, it's no impact here. So what you do in order to send packets here, when you have repeaters, you need to send 137% of the packets. You have to start here. Then you lose 10% here, you have 123 packets still here. He will send them 111%, you send losing 10%, 100% of the packets come here, everything is fine, if the code has not any inherent linear dependencies. So what does it tell you? In an end-to-end code, so what coding is doing today, the first link is not only carrying redundancy to survive its losses, it carries all the redundancy for later links as well. So why he has to do the burden? So conceptually, what is different here? We are sending 111, we are losing 10. We are buckling it up from 100 to 111, we are losing 10. We're buckling up to 111, losing 10, and you get 100 here. So what we do is here, we are looking at the packets, we are polishing up a little bit and send them onwards. So we are creating redundancy where it is needed. So imagine you have a very long chain and 0 losses, 0 losses, 0 losses, and the last link is error prone. So if you go to a server in the US and you sit on the Wi-Fi at your home, the Wi-Fi at your home is shaky, or the Wi-Fi at Starbucks is shaky. Now, they would create redundancy for all of the links. Everybody has to pay for the redundancy just for your last hop. With recoding, you could just say, okay, if the recoding would be on the access point at Starbucks, then everybody can send the minimum amount of data, and just before it happens, we are pulling up the redundancy and send it. This concept is not new, by the way, because they're actually doing it. But what they're doing is they build a proxy. And the proxy is doing exactly what we said before, full encode, decode. They stop all the packets and say, now I'm doing the encoding. And then they have the latency. Okay? So proxies in the internet are exactly trying to do something like this, which here is in a very easy way. Now, with the stuff of Notebook Deutsche Telekom, try to put some sources, right? What if you have 1 relay, 2, 3, repeater, recoder, what is the gain? Try it out, right? Look at the erasure rates, right? You can really try out, make your own plots, and maybe in the exercise we do something. But it's not only in the multi-hop. If you remember the gain where network coding shines, it's in multi-hop, but also in multipath. Here you see in another example, source and destination, you have something going over the A nodes, over the B nodes, over the C nodes down here, and you have some losses. So what is the capacity that you will see here? It's a question about min, cut, max flow again. What would you get if everybody has a recorder? Let's say like this. This is the easiest you can see.
Full recording gets you 90%.
On one of the links, but you have 3. So 2.7 more or less is the capacity, right? Yeah? So this is where the cuts are. You can do whatever you want. So if the numbers change a little bit, for example, if you have now a 0.4 here and it becomes more shaky, so do all the cuts, right? And if you do the cuts, where's the worst one? That's here, right? So 0.6, 0.7, 0.6 is 1.9. So this is what you get if this all recoders. Now if you would say, okay, let me do this, the forwarding, this is 80% by 90%, it's more or less 70%. By 60%, 40%, and by 90%, let's say 36% on this link, right? While network coding gives you 60% here on this link alone. So per link you can calculate it with and without recorder, and you see the advantage given here. So I think, therefore, if you see the symbol of the nice lady in the whiteboard there will be some exercise for that later. Right? Or you can find it on the notebook that we created for you. So you get these kind of throughput here, 1.9, and even without complex scheduling at the source. I will tell you later about this. So here's another example to say where are the losses, right? You always have to identify the max losses per flow. This is 20% here, 10, it doesn't matter where, and 10 where it doesn't matter it here, right? And then you sum it up and see if all of them have 10 megabit per second, you get an overall rate of 26 megabit per second. Quite easy. So here are some other recoding examples. Imagine you have one source here, one destination, and one relay repeater in the middle. But you also have this direct path. That makes it interesting. Often this direct path is very lossy because the one in the middle helps you a lot. The losses are shorter, are smaller. So now what you have here is to say, okay, what can I do here? If I send P1 and broadcast it, it will be received by the repeater, and it will be also received by him. So if I just forward this one again, P1, he will say, okay, it is successful, but it's useless because it's linear dependent. So the next time I'm broadcasting P2, the relay gets it, the other one didn't get it, I just forward it, all fine, right? Now if I send P3, he didn't get it, what should I send? P1, P2, linear combination? It will be linear dependent because he has already so many information. So here you don't know what he has. Now if you want to signal that and so on, that could be interesting. Now, if you do it from the beginning onwards with the coding, it's the same here. You would also create linear dependent stuff maybe. Other examples are source, destination. You have 50% losses on this side and 0% this. So what you can do in mesh, you can find one path. You say, okay, 50% here and 0% here. So if you say I can send one packet per time slot, how many time slots you need in mean to send the packets over? 3. So the likelihood is 50%, so twice here, but only once here, right? What you also can do is let them all receive the packets, right? Now the probability that none of them will get it is 6% more or less, right? But if then all of them are sending the packet out, then you have 4 transmissions here, right? So in this case, if 50% losses are, you send one broadcast, all of them receive it, mean value is that 2 will receive it, and forward it, you have 3 again. So there's no direct gain in that, but you can do something with that, just depending on the examples. So imagine you have in the source number of packets, you want to transmit it, and you send packet 1, packet 2, and both of them got it. So whatever they send out now to the destination will be linear dependent. Or they try to send different packets. And what is the likelihood that they send different packets? If he sends P1, the likelihood is 50% that he will send also P1, and only 50% P2. So if you give him the recoder at this point, you will randomly choose alpha and beta here, and gamma and delta over here, and then means with the randomness, we have no duplicates anymore. Okay? That is interesting. So this example again, if you have a source and you have only two packets, A, B, right? And you broadcast them. So if you have something here and he will go with A, he can go with A or B, so the success rate is only 50%, right? If you allow him to code also, his chances, if he sends A, he can send A, B, or a linear combination. It's a little bit better. But imagine they are just sending linear combination, success rate is 100%. It's 1. But there's something you could also do just with a simple XOR down here. What if you have 4 packets now? So he will send AB, and he will send A, B, C, D, or something like this. It's 50% as before. So the number has no impact here. But here it has an impact. It's 1 minus 2 over 15. Again, if you do then something like this, it's 100%. But also the generation size helps a little bit. And now the example, which is the most intriguing example for RLNC, multi-hop, multipath, and it has so many good examples that we should spend a little bit more time on that. And if you understand this, then I think you understood also where the impact of coding comes from. So here we have one source that would like to send 64 packets. And the destination would like to have those. The direct link from the source to the destination, 80% losses. So very unlikely that we get something through, but sometimes we get something through. Now, if this source is sending it to the relay, it will also to the destination, it will use the broadcast. So first the source will send something and say, here's one packet, broadcasting it. 40% losses towards the relays and later also recoders, and 60% on the next hop. And we need some kind of a medium access, right? Who can send what? And the idea is like this. First send the source, then the repeater 1, and then the repeater 2. Then the source, repeater 1, repeater 2, and so on, right? So the question is, how many times does the source need to send into broadcasting packets until the destination will say, I decoded fully? So the decoding probability depends on what? It will depend on the field size, for sure. We did this before, right? Even here, maybe. But it will also depend whether it's a repeater or a recoder here. So let's assume you use an RLNC end-to-end code or Reed-Solomon in the beginning with a repeater here. Okay? Then you will see, this is an inverse cumulative density function, the probability that you need more than 100, 110 whatever packets. This is the curve. And these two curves are the ones that are for the repeater. And it tells you, as a mean value, I put them here, 102 packets for a field of 2 to the 8. And a binary field, he needs 105 packets to send out. So here you see the impact of a field is not so big. It's only 3 packets difference, right? Doing the coding here or here. Now, when we switch, so now we say it's not Reed-Solomon or something. Now it's an RLNC encoder here, an RLNC decoder here, and now we use recoders here because the recoders will only use an RLNC context. And what happens, the numbers decrease significantly down to 76 and 81. So the difference between the low field and the high field is here 5 packets, a little bit more. So the minimum amount of packets the source should send is 64 packets. So even if there would be no losses, it would send 64. That would be here, right? Therefore, it starts here. Nothing is better than here. And now we are at 76, which is here, mean value. So we are not so far away from the optimal. But is this really a good result, or is this a bad result? What would you expect theoretically, how many packets we should have sent? This is code, all right. We just send a packet, recode the packets, send a packet, recode the packets, forwarding it. These are the losses. And we did it millions of times, so don't worry. Therefore, the curves are very nice. So we need 12 packets more than the optimal. Is this acceptable for such a lossy thing or not? What do you think? It's like in your master student thesis, or you need to discuss these results sometimes, right? You cannot just accept that and say, is this good or is it bad? So let me ask you something. What is the min, cut, max flow of this graph?
It's 1.
It's 1. What does it mean, 1?
We should ideally only need 64.
Very good. That shows that you understand more or less the problem of the whole thing, right? So the theory tells you with 64 packets and the recorders here, we should end up here. It's very hard to say what you would get with a repeater, right? Not really hard, but it's harder to read. For us, interesting, this is good, but we can do better. We can go to the minimum. Try this with, for example, with repeaters over here. You could even use repeaters, but you would need to understand, and you remember what we had in the butterfly. What have you sent? What will you send? All the signaling that goes up here, right? What do we need for the recoders? Nothing. They just take what they have and shoot. So how can we now improve the situation? And why didn't we get the optimal right away?
Because the expected value is basically, we don't only always hit the expected value, and we can never have less than it. So even though there is a chance that we get more than 64.
Why should we get more than 64 in the first place?
There's no point in being better than 64, but there is always a chance of being worse, therefore the average is shifted towards the worse.
Good, but my question is still valid. Why is it not always 64? Theory will tell us we get the min cut, right? We didn't get always the min cut. Sometimes we didn't get it. So which means, and this with code you can do, ask the decoder what he will get after each step. And he will tell you sometimes, I get duplicates. Where did he get duplicates from? And when? Why should he get duplicates? Anyway. You were already on the right track before. Not with what you said now, but 15 minutes before. So when I sent the first packet, and this luckily goes through, and they receive something, what can you ask to the decoder? You ask him, give me a new packet. He will recode, but he gets a copy of this. And if both are sending this and also luckily go through, he gets 3 times the same packet. So now it's not a matter of coding anymore. Now it becomes a problem of protocols. So we in the communication network chair, we are not doing so much information theory normally. We think about protocols. So now that we can handle the information theoretical part, it's very good, the ball is back in our game. So we need to understand when should they send packet, when should they start to send. And this is quite interesting. So again, I point you out to the Jupyter Notepad. There are some examples where you have a source destination with the direct link. Epsilon 3 is here towards some recoder relays, epsilon 1 and epsilon 2. Take this sheet, just fill it out and see what happens. I think it's very important that you get a feeling that what we do here actually works, right? This works later on your testbed, on Raspberry Pis. It works in some mininet context whatsoever. This is quite interesting.